The following is a conversation with Jim Keller, legendary microprocessor engineer who has worked at AMD, Apple, Tesla, and now Intel. He's known for his work on AMD K7, K8, K12, and Zen microarchitectures, Apple A4 and A5 processors, and co-author of the specification for the x86-64 instruction set and HyperTransport interconnect. He's a brilliant first principles engineer, an out-of-the-box thinker, and just an interesting and fun human being to talk to. This is the Artificial Intelligence Podcast. If you enjoy it, subscribe on YouTube, give it 5 stars on Apple Podcast, follow on Spotify, support it on Patreon, or simply connect with me on Twitter at Lex Fridman, spelled Fridman. I recently started doing ads at the end of the introduction. I'll do 1 or 2 minutes after introducing the episode and never any ads in the middle that can break the flow of the conversation. I hope that works for you and doesn't hurt the listening experience. This show is presented by Cash App, the #1 finance app in the App Store. I personally use Cash App to send money to friends, but you can also use it to buy, sell, and deposit Bitcoin in just seconds. Cash App also has a new investing feature. You can buy fractions of a stock, say $1 worth, no matter what the stock price is. Brokerage services are provided by Cash App Investing, a subsidiary of Square and member SIPC. I'm excited to be working with Cash App to support one of my favorite organizations called FIRST, best known for their FIRST robotics and Lego competitions. They educate and inspire hundreds of thousands of students in over 110 countries and have a perfect rating on Charity Navigator, which means that donated money is used to maximum effectiveness. When you get Cash App from the App Store or Google Play and use code LEXPODCAST, you'll get $10, and Cash App will also donate $10 to FIRST, which again is an organization that I've personally seen inspire girls and boys to dream of engineering a better world. And now, here's my conversation with Jim Keller. What are the differences and similarities between the human brain and a computer with the microprocessor at its core? Let's start with a philosophical question, perhaps.
Well, since people don't actually understand how human brains work, I think that's true.
I think that's true.
So it's hard to compare them. Computers are, there's really 2 things. There's memory and there's computation, right? And to date, almost all computer architectures are global memory, which is a thing, right? And then computation, where you pull data in, you do relatively simple operations on it and write data back.
So it's decoupled in modern computers, right. And you think in the human brain everything's a mess that's combined together.
What people observe is there's some number of layers of neurons which have local and global connections, and information is stored in some distributed fashion. And people build things called neural networks in computers where the information is distributed in some kind of fashion. There's a mathematics behind it. I don't know that the understanding of that is super deep. The computations we run on those are straightforward computations. I don't believe anybody has said a neuron does this computation. So to date, it's hard to compare them, I would say.
So let's get into the basics before we zoom back out. How do you build a computer from scratch? What is a microprocessor? What is a microarchitecture? What's an instruction set architecture? Maybe even as far back as what is a transistor?
So the special charm of computer engineering is there's a relatively good understanding of abstraction layers. So down at the bottom, you have atoms, and atoms get put together in materials like silicon or doped silicon or metal, and we build transistors. On top of that, we build logic gates, right? And then functional units, like an adder, a subtractor, or an instruction parsing unit, and then we assemble those into, processing elements. Modern computers are built out of, probably 10 to 20 locally, organic processing elements or coherent processing elements, and then that runs computer programs, right? So there's abstraction layers, and then software, there's an instruction set you run, and then there's assembly language, C, C++, Java, JavaScript, there's abstraction layers, essentially from the atom to the data center, right? So when you build a computer, first there's a target, like what's it for? Like how fast does it have to be? Which, today there's a whole bunch of metrics about what that is. And then in an organization of, 1,000 people who build a computer, there's lots of different disciplines that you have to operate on. Does that make sense? And so
there's a bunch of levels of abstraction in an organization like Intel and in your own vision. There's a lot of brilliance that comes in at every one of those layers. Some of it is science, some of it is engineering, some of it is art. What's the most, if you could pick favorites, what's the most important, your favorite layer on these layers of abstractions? Where does the magic enter this hierarchy?
I don't really care. That's the fun, I'm somewhat agnostic to that. So I would say for relatively long periods of time, instruction sets are stable. So the x86 instruction set, the ARM instruction set.
What's an instruction set?
So it says, how do you encode the basic operations? Load, store, multiply, add, subtract, conditional branch. There aren't that many interesting instructions. Like if you look at a program and it runs, 90% of the execution is on 25 opcodes, 25 instructions. And those are stable, right?
What does it mean stable?
Intel architecture has been around for 25 years.
It works.
It works. And that's because the basics, are defined a long time ago, right? Now, the way an old computer ran is you fetched instructions and you executed them in order. Do the load, do the add, do the compare. The way a modern computer works is you fetch large numbers of instructions, say 500, and then you find the dependency graph between the instructions, and then you execute in independent units those little micrographs. So a modern computer, like people like to say, computers should be simple and clean, but it turns out the market for simple, complete, clean, slow computers is zero, right? We don't sell any simple, clean computers. Now there's how you build it can be clean, but the computer people want to buy, that's say in a phone or a data center, fetches a large number of instructions, computes the dependency graph, and then executes it in a way that gets the right answers.
And optimizes that graph somehow.
Yeah,
so it executes it
they
fast.
run deeply out of order, and then there's semantics around how memory ordering works and other things work. So the computer sort of has a bunch of bookkeeping tables that says what order should these operations finish in or appear to finish in. But to go fast, you have to fetch a lot of instructions and find all the parallelism. Now, there's a second kind of computer, which we call GPUs today. And I call it the difference. There's found parallelism, like you have a program with a lot of dependent instructions. You fetch a bunch, and then you go figure out the dependency graph, and you issue instructions out of order. That's because you have one serial narrative to execute, which in fact can be done out of order.
Did you call it a narrative?
Yeah.
Wow.
So humans think in serial narrative. So read a book, right? There's a sentence after sentence after sentence, and there's paragraphs. Now you could diagram that. Imagine you diagrammed it properly, and you said, which sentences could be read in any order without changing the meaning, right? Like
That's a fascinating question to ask of a book. Yeah.
Yeah, you could do that. Right. So
theory,
some paragraphs could be reordered. Some sentences can be reordered. You could say, he is tall and smart and X, right? And it doesn't matter the order of tall and smart. But if you say the tall man is wearing a red shirt, what colors, like you can create dependencies, right?
Mm-hmm.
Right. And so GPUs, on the other hand, run simple programs on pixels, but you're given 1 million of them, and the first order, the screen you're looking at doesn't care which order you do it in. So I call that given parallelism. Simple narratives around the large numbers of things, where you can just say it's parallel because you told me it was.
So found parallelism where the narrative is sequential, but you discover like little pockets of parallelism versus
Turns out large pockets of parallelism.
large. So how hard is it to discover?
Well, how hard is it? That's just transistor count, right? So once you crack the problem, you say, here's how you fetch 10 instructions at a time. Here's how you calculate the dependencies between them. Here's how you describe the dependencies. Here's, these are pieces, right?
So once you describe the dependencies, then it's just a graph. Sort of, it's an algorithm that finds, well, what is that? I'm sure there's a graph theory, it's a theoretical answer here that's solvable. But in general, modern programs that human beings write, how much found parallelism is there in
About
them?
10x.
What does 10x mean?
So if you execute it in order,
versus, yeah.
You would get what's called cycles per instruction, and it would be about 3 cycles per instruction because of the latency of the operations and stuff. And a modern computer executes it like 0.25 cycles per instruction. So it's about, we today find 10x. And there's two things. One is the found parallelism in the narrative, right? Mm-hmm. And the other is the predictability of the narrative. Right. So certain operations say do a bunch of calculations, and if greater than 1, do this, else do that. That decision is predicted in modern computers to high 90% accuracy. So branches happen a lot. So imagine you have a decision to make every 6 instructions, which is about the average, right? But you want to fetch 500 instructions, figure out the graph, and execute them all in parallel. That means you have, let's say, if you fetch 600 instructions and it's every 6, you have to predict 99 out of 100 branches correctly for that window to be effective.
Okay, so parallelism, you can't parallelize branches, or you can.
No,
so
you can.
What does predict a
them.
branch mean? Well, what does predict?
So imagine you do a computation over and over. You're in a loop.
Yep.
So while n is greater than 1, do. And you go through that loop a million times. So every time you look at the branch, you say, it's probably still greater than 1.
And you're saying you could do that accurately?
Very accurately. Modern computers.
My mind is blown. How the heck do you do that? Wait a minute.
Well, you want to know? This is really sad. 20 years ago,
yes,
you simply recorded which way the branch went last time and predicted the same thing.
Right.
Okay.
What's the accuracy of that?
85%. So then somebody said, hey, let's keep a couple of bits and have a little counter. So when it predicts one way, we count up and then pins. So say you have a 3-bit counter. So you count up and then you count down. And if it's, you can use the top bit as the signed bit. So you have a signed 2-bit number. So if it's greater than 1, you predict taken, and less than 1, you predict not taken, right? Or less than 0, whatever the thing is. And that got us to 92%.
Oh.
Okay. No, it gets better. This branch depends on how you got there. So if you came down the code one way, you're talking about Bob and Jane, right? And then said, does Bob like Jane? It went one way. But if you're talking about Bob and Jill, does Bob like Jane? You go a different way, right? So that's called history. So you take the history and a counter. Mm-hmm. That's cool. But that's not how anything works today. They use something that looks a little like a neural network. So modern, you take all the execution flows, and then you do basically deep pattern recognition of how the program is executing. And you do that multiple different ways, and you have something that chooses what the best result is. There's a little supercomputer inside the computer
that's trying to predict
that
branching.
Calculates which way branches go. So the effective window that it's worth finding grass in gets bigger.
Why was that going to make me sad? Because that's amazing.
It's amazingly complicated.
Oh, wow.
Well, here's the funny thing. So to get to 85% took 1,000 bits. To get to 99% takes tens of megabits. So this is one of those, to get the result to get from a window of, say, 50 instructions to 500, it took 3 orders of magnitude or 4 orders of magnitude more bits.
Now, if you get the prediction of a branch wrong, What happens
You
then?
flush the pipe.
You flush the pipe, so it's just the performance cost.
But it gets even better.
Yeah.
So we're starting to look at stuff that says, so executed down this path, and then you had two ways to go, but far away, there's something that doesn't matter which path you went. So you took the wrong path, you executed a bunch of stuff. Mm-hmm. Then you had the mispredicting, you backed it up, but you remembered all the results you already calculated. Some of those are just fine. Like if you read a book and you misunderstand a paragraph, your understanding of the next paragraph sometimes is invariant to that understanding. Sometimes it depends on it.
And you can kind of anticipate that invariance.
Yeah, well, you can keep track of whether the data changed. And so when you come back through a piece of code, should you calculate it again or do the same thing?
Okay, how much of this is art and how much of it is science? Because it sounds pretty complicated. So,
well, how do you describe a situation? So imagine you come to a point in the road where you have to make a decision.
Yeah.
Right? And you have a bunch of knowledge about which way to go. Maybe you have a map. So you want to go the shortest way, or do you want to go the fastest way, or you want to take the nicest road? So there's some set of data.
Right.
So imagine you're doing something complicated like building a computer. And there's hundreds of decision points, all with hundreds of possible ways to go. And the ways you pick interact in a complicated way.
Right.
And then you have to pick the right spot.
Right. So
that art or science? I don't know.
You avoided the question. You just described the Robert Frost poem of Road Less Taken.
I described the Robert Frost problem. That's what we do as computer designers. It's all poetry.
Okay.
Great. Yeah, I don't know how to describe that because some people are very good at making those intuitive leaps. It seems like this combinations of things. Some people are less good at it, but they're really good at evaluating the alternatives, right? And everybody has a different way to do it. And some people can't make those leaps, but they're really good at analyzing it. So when you see computers are designed by teams of people who have very different skill sets. And a good team has lots of different kinds of people. And I suspect you would describe some of them as artistic, right, but not very many.
Unfortunately, or fortunately.
Fortunately. Well, computer design's hard. It's 99% perspiration.
And
the 1% inspiration is really important.
But you still need the 99.
Yeah, you got to do a lot of work. And then there are interesting things to do at every level of that stack. So
at the end of the day, if you run the same program multiple times, does it always produce the same result? Is there some room for fuzziness there?
That's a math problem. So if you run a correct C program, the definition is every time you run it, you get the same answer.
Yeah, that's a math statement.
But that's a language definitional statement. So
yes,
for years when we first did 3D acceleration of graphics, you could run the same scene multiple times and get different answers. Right. And then some people thought that was okay, and some people thought it was a bad idea. And then when the HPC world used GPUs for calculations, they thought it was a really bad idea. Okay. Now, in modern AI stuff, people are looking at networks where the precision of the data is low enough that the data is somewhat noisy. And the observation is the input data is unbelievably noisy. So why should the calculation be not noisy? And people have experimented with algorithms that say can get faster answers by being noisy. Like as the network starts to converge, if you look at the computation graph, it starts out really wide and then it gets narrower. And you can say, is that last little bit that important? Or should I start the graph on the next rev before we've whittled it all the way down to the answer, right? So you can create algorithms that are noisy. Now, if you're developing something and every time you run it, you get a different answer, it's really annoying. And so most people think, even today, every time you run the program, you get the same answer.
No, I know, but the question is, that's the formal definition of a programming language.
There is a definition of languages that don't get the same answer, but people who use those, you always want something because you get a bad answer, and then you're wondering, is it because
Right.
of something in the algorithm or because of this. And so everybody wants a little switch that says, no matter what,
Yeah.
do it deterministically. And it's really weird because almost everything going into modern calculations is noisy. So why
Right.
the answers have to be so clear? It's
Right. So where do you stand?
I design computers for people who run programs.
So
So if
you're
somebody says,
agnostic.
I want a deterministic answer, like most people want that.
Can you deliver a deterministic answer? I guess is the question. Like when you
Yeah, hopefully, sure.
that
What people don't realize is you get a deterministic answer even though the execution flow is very undeterministic. So
Right.
you run this
That's
program
the beauty
100
of it.
times. It never runs the same way twice, ever.
And the answer, it arrives at the same answer.
But it gets the same answer every time.
It's just amazing. Okay, you've achieved in the eyes of many people legend status as a chip architect. What design creation are you most proud of? Perhaps because it was challenging, because of its impact, or because of the set of brilliant ideas that that were involved in bringing it to
I
life.
find that description odd. And I have two small children,
Thank
and
you.
I promise you, they think it's hilarious.
This question,
Yeah. So
I do it for them.
so I am I'm really interested in building computers, and I've worked with really, really smart people. I'm not unbelievably smart. I'm fascinated by how they go together, both as a thing to do and as an endeavor that people do.
How people and computers go together.
Yeah, like how people think and build a computer. And I find sometimes that the best computer architects aren't that interested in people, or the best people managers aren't that good at designing computers.
So the whole stack of human beings is fascinating. So the managers, the individual engineers.
Yeah. So I said I realized after a lot of years of building computers, where you sort of build them out of transistors, logic gates, functional units, computational elements, that you could think of people the same way. So people are functional units.
Yes.
And then you could think of organizational design as a computer architectural problem. And then it's like, oh, that's super cool because the people are all different, just like the computational elements are all different. And they like to do different things. And so I had a lot of fun, like reframing how I think about organizations.
Just like with computers, we were saying execution paths. You can have a lot of different paths that end up at the same good destination. So what have you learned about the human abstractions from individual functional human units to the broader organization? What does it take to create something special?
Well, most people don't think simple enough. All right. So do you know the difference between a recipe and the understanding? There's probably a philosophical description of this. So imagine you're going to make a loaf of bread.
Yep.
The recipe says get some flour, add some water, add some yeast, mix it up, let it rise, put it in a pan, put it in the oven. It's a recipe, right? Understanding bread, you can understand biology, supply chains, grain grinders, yeast, physics, thermodynamics. Like there's so many levels of understanding there. And then when people build and design things, they frequently are executing some stack of recipes, right? And the problem with that is the recipes all have limited scope. Like if you have a really good recipe book for making bread, it won't tell you anything about how to make an omelet. Right. But if you have a deep understanding of cooking, right, then bread, omelets, sandwich, there's a different, way of viewing everything. And most people, when you get to be an expert at something, you're hoping to achieve deeper understanding, not just a large set of recipes to go execute. And it's interesting to walk groups of people because executing recipes is unbelievably efficient if it's what you want to do. If it's not what you want to do, you're really stuck. And that difference is crucial. And everybody has a balance of, let's say, deeper understanding of recipes. And some people are really good at recognizing when the problem is to understand something deeply. Does that make sense?
It totally makes sense. Does it every stage of development deep understanding on the team needed?
Oh, this goes back to the art versus science question.
Sure.
If you constantly unpacked everything for deeper understanding, you never get anything done.
Right.
And if you don't unpack understanding when you need to, you'll do the wrong thing. And then at every juncture, like human beings are these really weird things because everything you tell them has a million possible outputs, right? And then they all interact in a hilarious way.
Yeah, it's very
And
nice.
then having some intuition about what do you tell them, what do you do, when do you intervene, when do you not, it's complicated.
Right. So
It's essentially computationally unsolvable.
yeah, it's an intractable problem. Sure. Humans are a mess. But with deep understanding, do you mean also sort of fundamental questions of things like what is a computer, like, or why, like the why questions? Why are we even building this, like, of purpose? Or do you mean more like going towards the fundamental limits of physics, sort of really getting into the core of the science?
Well, in terms of building a computer, think a little simpler. So common practice is you build a computer, and then when somebody says, I want to make it 10% faster, you'll go in and say, all right, I need to make this buffer bigger, and maybe I'll add an add unit. Or, I have this thing that's 3 instructions wide. I'm going to make it 4 instructions wide. Right. And what you see is each piece gets incrementally more complicated, right? And then at some point you hit this limit, like adding another feature or buffer doesn't seem to make it any faster. And then people will say, well, that's because it's a fundamental limit. And then somebody else will look at it and say, well, actually the way you divided the problem up and the way that different features are interacting is limiting you, and it has to be rethought, rewritten, right? So then you refactor it and rewrite it, and what people commonly find is the rewrite is not only faster, but half as complicated.
From scratch?
Yes.
So how often in your career, but just have you seen as needed, maybe more generally, to just throw the whole thing out? And
this is where I'm on one end of it, every 3 to 5 years.
Which end are you on? Wait.
Rewrite more often.
Rewrite, and 3 to 5 years is...
So if you want to really make a lot of progress on computer architecture, every 5 years you should do one from scratch.
So where does the x86 64 standard come in? Well, how often do you...
Well, I was the co-author of that spec in 98. That's 20 years ago.
Yeah, so that's still around.
The instruction set itself has been extended quite a few times.
Yes.
And instruction sets are less interesting than the implementation underneath. There's been, on x86 architecture, Intel's designed a few, AMD's designed a few, very different architectures. And I don't want to go into too much of the detail about how often, but there's a tendency to rewrite it every 10 years, and it really should be every 5.
So you're saying you're an outlier in that sense.
Rewrite more often.
Rewrite more often.
Well, and
isn't it scary?
Yeah, of course. Well, scary to who?
To everybody involved, because like you said, repeating the recipe is efficient. Companies want to make money. Well, no, individual engineers want to succeed, so you want to incrementally increase the buffer from 3 to 4.
So this is where you get into diminishing return curves. I think Steve Jobs said this, right? So you have a project and you start here and it goes up and you have diminishing return.
Yep.
And to get to the next level, you have to do a new one, and the initial starting point will be lower than the old optimization point, but it'll get higher. So now you have 2 kinds of fear: short-term disaster and long-term disaster.
And you're
grown-ups, right?
Yes.
Like, people with a quarter-by-quarter business objective are terrified about changing everything.
Yeah.
And people who are trying to run a business or build a computer for a long-term objective know that the short-term limitations block them from the long-term success. So if you look at leaders of companies that had really good long-term success, every time they saw that they had to redo something, they did.
And so somebody has to speak up.
Or you do multiple projects in parallel. Like you optimize the old one while you build a new one. But the marketing guys are always like, promise me that the new computer is faster on every single thing. And the computer architect says, well, the new computer will be faster on the average. But there's a distribution of results and performance, and you'll have some outliers that are slower. And that's very hard because they have one customer who cares about that one.
So speaking of the long term, for over 50 years now, Moore's Law has served for me and millions of others as an inspiring beacon of what kind of amazing future brilliant engineers can build.
Yep.
I'm just making your kids laugh all of today.
That was great.
So first, in your eyes, what is Moore's Law, if you could define for people who don't know?
Well, the simple statement from Gordon Moore was double the number of transistors every 2 years, something like that. And then my operational model is we increase the performance of computers by 2x every 2 or 3 years. And it's wiggled around substantially over time. And also in how we deliver performance has changed.
So, right.
But
so
the foundational idea was 2x the transistors every 2 years. The current cadence is something like, they call it a shrink factor, like 0.6 every 2 years, which is not 0.5.
But that's referring strictly, again, to the original definition
of transistor count.
A shrink factor is just getting them smaller and smaller and smaller.
Well, as you for a constant chip area,
right. If
you make the transistors smaller by 0.6, then you get 1 over 0.6 more transistors.
So can you linger on it a little longer? What do you think should be the broader definition of Moore's Law? When you mentioned how you think of performance, just broadly, what's a good way to think about Moore's Law?
Well, first of all, so I've been aware of Moore's Law for 30 years.
In which sense?
Well, I've been designing computers for 40.
You're just watching it before your eyes kind of thing.
Well, and somewhere where I became aware of it, I was also informed that Moore's Law was going to die in 10 to 15 years. And I thought that was true at first, but then after 10 years, it was going to die in 10 to 15 years. And then at one point, it was going to die in 5 years. And then it went back up to 10 years. And at some point, I decided not to worry about that particular prognostication for the rest of my life, which is fun. And then I joined Intel, and everybody said Moore's Law is dead.
Right.
And I thought that's sad because it's the Moore's Law company. And it's not dead, and it's always been going to die. And, humans like these apocryphal kind of statements like, we'll run out of food, or we'll run out of air, or run out of room, or we'll run out of, something.
Right, but it's still incredible that it's lived for as long as it has. And yes, there's many people who believe now that Moore's Law is dead.
They can join the last 50 years of people who had the same idea.
There's a long tradition. But why do you think, if you can try to understand it, why do you think it's not dead?
Well, first,
currently,
let's just think, people think Moore's Law is one thing. Transistors get smaller. But actually under the sheet, there's literally thousands of innovations. And almost all those innovations have their own diminishing return curves. Yep. So if you graph it, it looks like a cascade of diminishing return curves. I don't know what to call that. But the result is an exponential curve. Well, at least it has been. So, and we keep inventing new things. So if you're an expert in one of the things on a diminishing return curve, right, and you can see its plateau, you will probably tell people, well, this is done. Meanwhile, some other pile of people are doing something different. So that's just normal. So then there's the observation of how small could a switching device be? So a modern transistor is something like 1,000 by 1,000 by 1,000 atoms, right? And you get quantum effects down around 2 to 10 atoms. So you can imagine a transistor as small as 10 by 10 by 10. So that's 1,000,000 times smaller. And then the quantum computational people are working away at how to use quantum effects. So
1,000 by 1,000 by 1,000
atoms.
That's a really clean way of putting it.
Well, a fin, like a modern transistor, if you look at the fin, it's like 120 atoms wide, but we can make that thinner. And then there's a gate wrapped around it, and then there's spacing. There's a whole bunch of geometry. And, a competent transistor designer could count both atoms in every single direction. Like there's techniques now to already put down atoms in a single atomic layer, right? And you can place atoms if you want to. It's just, from a manufacturing process, if placing an atom takes 10 minutes and you need to put, 10 to the 23rd atoms together to make a computer, it would take a long time. So the methods are, both shrinking things and then coming up with effective ways to control what's happening.
Manufacture stably and cheaply.
Yeah. So the innovation stack's pretty broad. There's equipment, there's optics, there's chemistry, there's physics, there's material science, there's metallurgy. There's lots of ideas about when you put different materials together, how do they interact? Are they stable? Are they stable over temperature? Like, are they repeatable? There's literally thousands of technologies involved.
But just for the shrinking, you don't think we're quite yet close to the fundamental limits of physics?
I did a talk on Moore's Law, and I asked for a roadmap to a path of 100, and after 2 weeks, they said we only got to 50.
100 what, sorry?
100x shrink.
100x shrink? We only got to
50. And I said, why don't you give it another 2 weeks? Well, here's the thing about Moore's Law, right? So I believe that the next 10 or 20 years of shrinking is going to happen, right? Now, as a computer designer, you have two stances. You think it's going to shrink, in which case you're designing and thinking about architecture in a way that you'll use more transistors. Or conversely, not be swamped by the complexity of all the transistors you get, right? You have to have a strategy,
So you're open to the possibility and waiting for the possibility of a whole new army of transistors ready to work.
I'm expecting more transistors every 2 or 3 years by a number large enough that how you think about design, how you think about architecture has to change. Like imagine you build brick buildings out of bricks, and every year the bricks are half the size, or every 2 years. Well, if you kept building bricks the same way, so many bricks per person per day, the amount of time to build a building would go up exponentially. Right. But if you said, I know that's coming, so now I'm going to design equipment that moves bricks faster, uses them better, because maybe you're getting something out of the smaller bricks, more strength, thinner walls, less material, efficiency out of that. So once you have a roadmap with what's going to happen, transistors, we're going to get more of them. Then you design all this collateral around it to take advantage of it and also to cope with it. Like that's the thing people don't understand. It's like if I didn't believe in Moore's Law and then Moore's Law transistors showed up, my design teams were all drowned.
So what's the hardest part of this inflood of new transistors? I mean, even if you just look historically throughout your career, what's the thing? What fundamentally changes when you add more transistors in the task of designing an architecture?
Well, there's two constants, right? One is people don't get smarter. I think.
By the way, there's some science showing that we do get smarter, but because of nutrition, whatever.
Yeah.
Sorry to bring that.
Flynn effect.
Yes.
Yeah, exactly. I'm familiar with it. Nobody understands it. Nobody knows if it's still going on. So that's
or whether it's real or not. But
I sort of.
Anyway, but not exponentially.
I would believe for the most part, people aren't getting much smarter.
The evidence doesn't support it. That's right.
And then teams can't grow that much.
Right.
So human beings, we're really good in teams of 10, up to teams of 100. They can know each other. Beyond that, you have to have organizational boundaries. So those are pretty hard constraints, right? So then you have to divide and conquer. Like as the designs get bigger, you have to divide it into pieces. The power of abstraction layers is really high. We used to build computers out of transistors. Now we have a team that turns transistors into logic cells and another team that turns them into functional units, another one that turns them into computers, right? So we have abstraction layers in there. And you have to think about when do you shift gears on that. We also use faster computers to build faster computers. So some algorithms run twice as fast on new computers, but a lot of algorithms are n squared. So, a computer with twice as many transistors and it might take 4 times as long to run. So you have to refactor the software. Like simply using faster computers to build bigger computers doesn't work.
So
you have to think about all these things.
So in terms of computing performance and the exciting possibility that more powerful computers bring, is shrinking the thing we've just been talking about one of the biggest exciting possibilities of advancement in performance, or is there other directions that you're interested in, like in the direction of sort of enforcing given parallelism, or like doing massive parallelism in terms of many CPUs, stacking CPUs on top of each other, that kind of parallelism, or any kind of other parallelism?
Well, think about it a different way. So old computers, slow computers, you said A equal B plus C times D. Pretty simple, right? And then we made faster computers with vector units, and you can do proper equations and matrices, right? And then modern like AI computations or like convolutional neural networks, where you convolve one large data set against another. And so there's sort of this hierarchy of mathematics, from simple equation to linear equations to matrix equations to deeper kind of computation. And the data sets are getting so big that people are thinking of data as a topology problem. Data is organized in some immense shape. And then the computation, which sort of wants to be get data from immense shape and do some computation on it. So what computers have allowed people to do is have algorithms go much further. So that paper you reference, the Sutton paper, they talked about, like when AI started, it was apply rule sets to something. That's a very simple computational situation. And then when they did first chess thing, they solved deep searches. So have a huge database of moves and results, deep search, but it's still just a search. Right? Now we take large numbers of images and we use it to train these weight sets that we convolve across. It's a completely different kind of phenomena. We call that AI. And now they're doing the next generation. And if you look at it, they're going up this mathematical graph, right? And then computations, both computation and data sets support going up that graph.
Yeah, the kind of computation though I would argue that all of it is still a search, right? Just like you said, a topology problem of data sets, you're searching the data sets for valuable data, and also the actual optimization of neural networks is a kind of search for
I don't know, if you had looked at the inner layers of finding a cat, it's not a search. It's a set of endless projections. So, a projection is, here's a shadow of this phone.
Yeah.
Right? And then you can have a shadow of that onto something, a shadow on that of something. And if you look in the layers, you'll see this layer actually describes pointy ears and round eyedness and fuzziness. But the computation to tease out the attributes is not search.
Right.
Like the inference part might be search, but the training's not search.
Okay. Well,
and then in deep networks, they look at layers and they don't even know it's represented. And yet, if you take the layers out, it doesn't work.
Okay, so
I don't think it's search.
All right, well.
But you have to talk to a mathematician about what that actually is.
Well, we could disagree, but it's just semantics. I think it's not, but it's certainly not.
I would say it's absolutely not semantics, but.
Okay. All right. Well, if you want to go there, so optimization to me is search, and we're trying to optimize the ability of a neural network to detect cat ears. And the difference between chess and the space, the incredibly multi-dimensional, 100,000 dimensional space that neural networks are trying to optimize over, is nothing like the chessboard database. Yeah. So it's a totally different kind of thing. And in that sense, you can say it loses the meaning.
I can see how you might say if you. The funny thing is, it's the difference between given search space and found search space.
Right, exactly.
Yeah, maybe that's a different way to describe it.
That's a beautiful way to put it. Okay. But you're saying, what's your sense in terms of the basic mathematical operations and the architectures, hardware that enables those operations? Do you see the CPUs of today still being a really core part of executing those mathematical operations?
Yes. Well, the operations, continue to be add, subtract, load, store, compare, and branch. It's remarkable. So it's interesting that the building blocks of computers are transistors, and under that atoms. So you got atoms, transistors, logic gates, computers, right? Functional units of computers. The building blocks of mathematics at some level are things like adds and subtracts and multiplies, but the space mathematics can describe is, I think, essentially infinite. But the computers that run the algorithms are still doing the same things. Now, a given algorithm might say, I need sparse data, or I need 32-bit data, or I need, like a convolution operation that naturally takes 8-bit data, multiplies it, and sums it up a certain way. So the data types in TensorFlow imply an optimization set, but when you go right down and look at the computers, it's AND and OR gates doing adds and multiplies. Like that hasn't changed much. Now the quantum researchers think they're going to change that radically, and then there's people who think about analog computing, because you look in the brain and it seems to be more analogish, that maybe there's a way to do that more efficiently. But we have a million X on computation, and I don't know the relationship between computational, let's say, intensity and ability to hit mathematical abstractions. I don't know any ways to describe that, but just like you saw in AI, you went from rule sets to simple search to complex search to, say, found search. Mm-hmm. Like those are, orders of magnitude more computation to do. And as we get the next 2 orders of magnitude, like a friend, Raja Gadori, said, every order of magnitude changes the computation.
It fundamentally changes what the computation is doing.
Yeah. Oh, the expression, the difference in quantity is a difference in kind. The difference between ant and anthill, right? Or neuron and brain. There's this indefinable place where the quantity changed the quality, right? And we've seen that happen in mathematics multiple times, and my guess is it's going to keep happening.
So in your sense is, if you focus head down and shrinking the transistor.
Well, it's not just head down. We're aware of the software stacks that are running in the computational loads, and we're kind of pondering, what do you do with a petabyte of memory that wants to be accessed in a sparse way and have, the kind of calculations AI programmers want. So there's a dialogue and interaction, but when you go in the computer chip, you find adders and subtractors and multipliers. And
so if you zoom out then with, as you mentioned, Ray Sutton, the idea that most of the development in the last many decades in AI research came from just leveraging computation and just simple algorithms waiting for the computation to improve.
Well, software guys have a thing that they call it the problem of early optimization.
Right.
So you write a big software stack, and if you start optimizing the first thing you write, the odds of that being the performance limiter is low.
Right.
But when you get the whole thing working, can you make it 2x faster by optimizing the right things? Sure. While you're optimizing that, could you have written a new software stack, which would have been a better choice? Maybe. Now you have creative tension. So,
but the whole time as you're doing the writing, that's the software we're talking about. The hardware underneath gets faster and faster.
Well, this goes back to the Moore's Law. If Moore's Law is going to continue, then your AI research should expect that to show up, and then you make a slightly different set of choices. Then we've hit the wall, nothing's going to happen, and from here it's just us rewriting algorithms. That seems like a failed strategy for the last 30 years of Moore's Law's death. So
can you just linger on it? I think you've answered it, but I'll just ask the same dumb question over and over. So why do you think Moore's Law is not going to die? Which is the most promising, exciting possibility of why it won't die in the next 5-10 years? So is it the continued shrinking of the transistor, or is it another S-curve that steps in and it totally sort of...
Well, the shrinking the transistor is literally thousands of innovations.
Right. So there's
So
there's stacks of S curves in there.
there's a whole bunch of S curves just kind of running their course and being reinvented and new things. The semiconductor fabricators and technologists have all announced what's called nanowires. So they took a fin which had a gate around it and turned that into little wires, so you have better control of that, and they're smaller. And then from there's some obvious steps about how to shrink that. The metallurgy around wire stacks and stuff has very obvious abilities to shrink. And, there's a whole combination of things there to do.
Your sense is that we're going to get a lot if this innovation from just that shrinking.
Yeah, like a factor of 100 is a lot.
Yeah, I would say that's incredible. And it's totally unknown.
It's only 10 or 15 years.
Now, you're smarter, you might know, but to me, it's totally unpredictable of what that 100x would bring in terms of the nature of the computation that people would be
you're familiar with Bell's law. So for a long time, it was mainframes, minis, workstation, PC, mobile.
Yeah.
Moore's law drove faster, smaller computers, right? And then when we were thinking about Moore's law, Raja Gadori said every 10x generates a new computation. So scalar, vector, matrix, topological computation, right? And if you go look at the industry trends, there was mainframes and mini computers and PCs, and then the internet took off, and then we got mobile devices, and now we're building 5G wireless with 1 millisecond latency. Yeah. And people are starting to think about the smart world where everything knows you, recognizes you. Like the transformations are going to be like unpredictable.
How does it make you feel that you're one of the key architects of this kind of future? So we're not talking about the architects of the high level people who build the Angry Bird apps and
What's wrong with Angry Bird apps? Who knows? Maybe that's the whole point of the universe.
I'm going to take a stand at that and the attention distracting nature of mobile phones. I'll take a stand. But anyway, in terms of
that matters much.
The side effects of smartphones or the attention distraction, which part?
Well, who knows? Where this is all leading? It's changing so fast.
Wait, so back to
my parents used to yell at my sisters for hiding in the closet with a wired phone with a dial on it. Stop talking to your friends all day.
Right.
Now my wife yells at my kids for talking to their friends all day on text. It looks the same to me.
It's echoes of the same thing. Okay, but you are one of the key people architecting the hardware of this future. How does that make you feel? Do you feel responsible? Do you feel excited?
So we're in a social context. So there's billions of people on this planet. There are literally millions of people working on technology. I feel lucky to be, doing what I do and getting paid for it, and there's an interest in it. But there's so many things going on in parallel. It's like the actions are so unpredictable. If I wasn't here, somebody else would do it. The vectors of all these different things are happening all the time. There's I'm sure some philosopher or meta-philosophers, wondering about how we transform our world.
So you can't deny the fact that these tools, these tools are changing our world.
That's right.
So do you think it's changing for the better?
I read this thing recently. It said the two disciplines with the highest GRE scores in college are physics and philosophy, right? And they're both sort of trying to answer the question, why is there anything, right? And the philosophers, are on the kind of theological side, and the physicists are obviously on the, the material side. And there's 100 billion galaxies with 100 billion stars. It seems, repetitive at best. So there's on our way to 10 billion people. I mean, it's hard to say what it's all for, if that's what you're asking.
Yeah, I guess I am.
Things do tend to significantly increases in complexity, and I'm curious about how computation, like our world, our physical world, inherently generates mathematics. It's kind of obvious, right? So we have XYZ coordinates. You take a sphere, you make it bigger. You get a surface that falls, grows by r squared. Like, it generally generates mathematics, and the mathematicians and the physicists have been having a lot of fun talking to each other for years. And computation has been, let's say, relatively pedestrian. Like, computation in terms of mathematics has been doing binary algebra, while those guys have been gallivanting through the nether realms of possibility, right? And now recently, the computation lets you do mathematical computations that are sophisticated enough that nobody understands how the answers came out, right?
Machine learning.
Yeah. Right. It used to be you get data set, you guess at a function. The function is considered physics if it's predictive of new functions, new data sets. Modern, you can take a large data set with no intuition about what it is and use machine learning to find a pattern that has no function, right? And it can arrive at results that I don't know if they're completely mathematically describable. So computation has kind of done something interesting compared to A equal B plus C.
There's something reminiscent of that step from the basic operations of addition to taking a step towards neural networks that's reminiscent of what life on Earth at its origins was doing. Do you think we're creating sort of the next step in our evolution in creating artificial intelligence systems that will...
I don't know. I mean, there's so much in the universe already, it's hard to say.
Where we stand in this whole thing.
Are human beings working on additional abstraction layers and possibilities? Yeah, it appears so. Does that mean that human beings don't need dogs? No. Like there's so many things that are all simultaneously interesting and useful.
But you've seen, throughout your career, you've seen greater and greater level abstractions built in artificial machines, right? Do you think, when you look at humans, do you think that look of all life on Earth as a single organism building this thing, this machine with greater and greater levels of abstraction? Do you think humans are the peak, the top of the food chain in this long arc of history on Earth? Or do you think we're just somewhere in the middle? Are we the basic functional operations of a CPU? Are we the C++ program, the Python program, or with the neural network? Or...
Like somebody's, people have calculated like how many operations does the brain do? And something, I've seen the number 10 to the 18th a bunch of times, arrive different ways. So could you make a computer that did 10 to the 20th operations?
Yes.
Sure.
Right. So you think...
We're going to do that. Now, is there something magical about how brains compute things? I don't know. My personal experience is interesting because you think you know how you think, and then you have all these ideas and you can't figure out how they happened. And if you meditate, what you can be aware of is interesting. So I don't know if brains are magical or not. The physical evidence says no. Lots of people's personal experience says yes. So what would be funny is if brains are magical and yet we can make brains with more computation. I don't know what to say about that, but...
Well, do you think magic is an emergent phenomena? What
could be. I have no explanation for it. I'm
let me ask Jim Keller of what in your view is consciousness?
What's consciousness?
Yeah, like what consciousness, love, things that are these deeply human things that seems to emerge from our brain. Is that something that we'll be able to encode in chips that get faster and faster and faster and faster?
That's like a 10-hour conversation. Nobody really knows.
Can you summarize it in a couple of
words?
Sentences?
Many people have observed that organisms run at lots of different levels, right? If you had two neurons, somebody said you'd have one sensory neuron and one motor neuron, right? So we move towards things and away from things, and we have physical integrity and safety or not, right? And then if you look at the animal kingdom, you can see brains that are a little more complicated. And at some point there's a planning system, and then there's an emotional system that's, happy about being safe or unhappy about being threatened, right? And then our brains have massive numbers of structures, like planning and movement and thinking and feeling and drives and emotions. And we seem to have multiple layers of thinking systems. And we have a dream system that nobody understands whatsoever, which I find completely hilarious. And you can think in a way that those systems are more independent, and you can observe, the different parts of yourself can observe them. I don't know which one's magical. I don't know which one's not computational. So,
is it possible that it's all computation?
Probably. Is there a limit to computation? I don't think so.
Do you think the universe is a computer?
It seems to be. It's a weird kind of computer, because if it was a computer, right, like when they do calculations on how much calculation it takes to describe quantum effects is unbelievably high.
Right.
So if it was a computer, wouldn't you have built it out of something that was easier to compute? Right. It's a funny system. But then the simulation guys have pointed out that the rules are kind of interesting. Like when you look really close, it's uncertain. And the speed of light says you can only look so far. Mm-hmm. And things can't be simultaneous except for the odd entanglement problem where they seem to be. Like the rules are all kind of weird.
Yeah.
And somebody said physics is like having 50 equations with 50 variables to define 50 variables. Like, it's like physics itself has been a shit show for thousands of years. It seems odd when you get to the corners of everything. It's either uncomputable or undefinable or uncertain.
It's almost like the designers of the simulation are trying to prevent us from understanding it perfectly.
But also the things that require calculations require so much calculation that our idea of the universe of a computer is absurd, because every single little bit of it takes all the computation in the universe to figure out. So that's a weird kind of computer. You say the simulation is running in a computer, which has, by definition, infinite computation.
Not infinite. Oh, you mean if the universe is infinite?
Well, every little piece of our universe seems to take infinite computation to figure out.
Just a lot.
Well, a lot's a pretty big number. Compute this little teeny spot takes all the mass in the local 1 light year by 1 light year space. It's close enough to infinite. So.
Oh, it's a heck of a computer if it is one.
I know it's a weird description, because the simulation description seems to break when you look closely at it. But the rules of the universe seem to imply something's up. That seems a little arbitrary.
The universe, the whole thing, the laws of physics.
Yeah.
It just seems like how did it come out to be the way it is?
But lots of people talk about that. It's like I said, the two smartest groups of humans are working on the same problem
from different
aspects, and they're both complete failures. So that's kind of cool.
They might succeed eventually.
After 2,000 years, the trend isn't good.
Well, 2,000 years is nothing in the span of the history of the universe, so fair. We have some time.
But the next 1,000 years doesn't look good either. So
that's what everybody says at every stage. But with Moore's law, as you've just described, not being dead, the exponential growth of technology, the future seems pretty incredible.
Well, it'll be interesting, that's for sure.
That's right. So what are your thoughts on Ray Kurzweil's sense that exponential improvement in technology will continue indefinitely? Is that how you see Moore's law? Do you see Moore's law more broadly, in the sense that technology of all kinds has a way of stacking S-curves on top of each other where it'll be exponential, and then we'll see all kinds of...
What does an exponential of 1 million mean? That's a pretty amazing number. And that's just for a local little piece of silicon. Now let's imagine you, say, decided to get 1,000 tons of silicon to collaborate in one computer at 1 million times the density. Like now you're talking, I don't know, 10 to the 20th more computation power than our current already unbelievably fast computers. Like nobody knows what that's going to mean. The sci-fi guys call it, computronium. Like when a local civilization turns the nearby star into a computer.
Right.
Like, I don't know if that's true, but...
So just even when you shrink the transistor,
that's only one dimension.
The ripple effects of that.
Like people tend to think about computers as a cost problem, right? So computers are made out of silicon and minor amounts of metals. and, this and that. None of those things cost any money. Like, there's plenty of sand. Like you could just turn the beach and a little bit of ocean water into computers. So all the cost is in the equipment to do it. And the trend on equipment is, once you figure out how to build the equipment, the trend of cost is zero. Elon said, first you figure out what configuration you want the atoms in, and then how to put them there. Right?
Yeah.
Because,
right.
Here's right. His great insight is, people are how constrained. I have this thing, I know how it works, and then little tweaks to that will generate something, as opposed to what do I actually want, and then figure out how to build it. It's a very different mindset, and almost nobody has it, obviously.
Well, let me ask on that topic. You were one of the key early people in the development of Autopilot, at least in the hardware side. Elon Musk believes that Autopilot and vehicle autonomy, if you just look at that problem, can follow this kind of exponential improvement. In terms of the how question that we're talking about, there's no reason why it can't. What are your thoughts on this particular space of vehicle autonomy, and you're part of it, and Elon Musk's and Tesla's vision for vehicle
the
autonomy?
computer you need to build was straightforward. And you could argue, well, does it need to be 2 times faster or 5 times or 10 times? But that's just a matter of time or price in the short run. So that's not a big deal. You don't have to be especially smart to drive a car. So it's not like a super hard problem. I mean, the big problem with safety is attention, which computers are really good at, not skills.
Well, let me push back on one. You say everything you said is correct, but we as humans tend to take for granted how incredible our vision system is. So
you can drive a car with 20/50 vision, and you can train a neural network to extract the distance of any object and the shape of any surface from a video and data.
Yeah, but
it's really simple.
No, it's not simple.
That's a simple data problem.
It's not simple. It's because it's not just detecting objects, it's understanding the scene, and it's being able to do it in a way that doesn't make errors. So the beautiful thing about the human vision system and our entire brain around the whole thing is we're able to fill in the gaps. It's not just about perfectly detecting cars. It's inferring the occluded cars. It's trying to. It's understanding the
I think that's mostly a data problem.
So you think with data, with compute, with improvement in computation, with improvement in collection.
Well, there's when you're driving a car and somebody cuts you off, your brain has theories about why they did it. Right. They're a bad person. They're distracted. They're dumb. You can listen to yourself, right? So, if you think that narrative is important to be able to successfully drive a car, then current autopilot systems can't do it. But if cars are ballistic things with tracks and probabilistic changes of speed and direction, and roads are fixed and given, by the way, they don't change dynamically, right? You can map the world really thoroughly. You can place every object really thoroughly. Right. You can calculate trajectories of things really thoroughly. Right.
But everything you said about really thoroughly has a different degree of difficulty. So,
and you could say at some point, computer autonomous systems will be way better at things that humans are lousy at. They'll be better at attention. They'll always remember there was a pothole in the road that humans keep forgetting about. They'll remember that this set of roads has these weirdo lines on it that the computers figured out once, and especially if they get updates, so if somebody changes a given,
right?
The key to robots and stuff, somebody said, is to maximize the givens, right?
right.
So having a robot pick up this bottle cap is way easier if you put a red dot on the top, because then you have to figure out, and if you want to do a certain thing with it, maximize the givens is the thing. And autonomous systems are happily maximizing the givens. Like humans, when you drive someplace new, you remember it because you're processing it the whole time. And after the 50th time you drove to work, you get to work, you don't know how you got there, right? You're on autopilot, right? Autonomous cars are always on autopilot. But the cars have no theories about why they got cut off or why they're in traffic.
So
they
that's
also never stop paying attention.
right. So I tend to believe you do have to have theories, mental models of other people, especially with pedestrian and cyclists, but also with other cars. So everything you said is is actually essential to driving. Driving is a lot more complicated than people realize, I think. So sort of to push back slightly, but to
cut into traffic, right?
Yep.
You can't just wait for a gap. You have to be somewhat aggressive.
Yeah.
You'll be surprised how simple a calculation for that is.
I may be on that particular point, but there's maybe I actually have to push back. I would be surprised. You know what? Yeah, I'll just say where I stand. I would be very surprised, but I think you might be surprised how complicated it is.
I tell people it's like progress disappoints in the short run, surprises in the long run.
It's very possible.
I suspect in 10 years it'll be just like taken for granted.
Yeah, probably. But you're probably right, and I'll look like
it's going to be a $50 solution that nobody cares about. It's like GPSs. Like, wow, GPSs. We have satellites in space that tell you where your location is. It was a really big deal. Now everything has a GPS in it.
Yeah, that's true. But I do think that systems that involve human behavior are more complicated than we give them credit for. So we can do incredible things with technology that don't involve humans, but when
I think humans are less complicated than people, frequently ascribe.
Maybe we
tend to operate out of large numbers of patterns and just keep doing it over and over.
But I can't trust you because you're a human. That's something a human would say. But my hope is on the point you've made is even if no matter who's right, I'm hoping that there's a lot of things that humans aren't good at that machines are definitely good at, like you said, attention and things like that. Well, they'll be so much better that the overall picture of safety and autonomy will be obviously cars will be safer, even if they're not as good at understanding.
I'm a big believer in safety. I mean, there are already the current safety systems like cruise control that doesn't let you run into people and lane keeping. There are so many features that you just look at the Pareto of accidents and knocking off like 80% of them is, super doable.
Just to linger on the Autopilot team and the efforts there, it seems to be that there's a very intense scrutiny by the media and the public in terms of safety, the pressure, the bar put before autonomous vehicles. What are your sort of, as a person there working on the hardware and trying to build a system that builds a safe vehicle and so on, what was your sense about that pressure? Is it unfair? Is it expected of new technology?
Yeah, it seems reasonable. I was interested. I talked to both American and European regulators, and I was worried that the regulations would write into the rules technology solutions. Like modern brake systems imply hydraulic brakes. So if you read the regulations, to meet the letter of the law for brakes, it sort of has to be hydraulic. Right, and the regulator said they're interested in the use cases, like a head-on crash, an offset crash. Don't hit pedestrians. Don't run into people. Don't leave the road. Don't run a red light or a stoplight. They were very much into the scenarios, and and they had all the data about which scenarios injured or killed the most people, and for the most part, those conversations were like, what's the right thing to do to take the next step. Now, Elon's very interested also in the benefits of autonomous driving are freeing people's time and attention as well as safety. And I think that's also an interesting thing. But, building autonomous systems so they're safe and safer than people seemed, since the goal is to be 10x safer than people, having the bar to be safer than people and scrutinizing accidents seems philosophically correct. So I think that's a good thing.
It's different than the things you worked at, the Intel, AMD, Apple, with Autopilot chip design and hardware design. What are interesting or challenging aspects of building this specialized kind of computing system in the automotive space?
I mean, there's two tricks to building like an automotive computer. One is the software team, the machine learning team, is developing algorithms that are changing fast. Yeah. So as you're building the accelerator, you have this, worry or intuition that the algorithms will change enough that the accelerator will be the wrong one. right? And there's the generic thing, which is if you build a really good general purpose computer, say its performance is 1, and then GPU guys will deliver about 5x the performance for the same amount of silicon, because instead of discovering parallelism, you're given parallelism. And then special accelerators get another 2 to 5x on top of a GPU, because you say, I know the math is always 8-bit integers into 32-bit accumulators, and the operations are the subset of mathematical possibilities. So AI accelerators have a claimed performance benefit over GPUs because in the narrow math space, you're nailing the algorithm. Now, you still try to make it programmable, but the AI field is changing really fast. So there's a little creative tension there of, I want the acceleration afforded by specialization without being over specialized, so that the new algorithm is so much more effective that you would have been better off on a GPU. So there's a tension there. To build a good computer for an application like automotive, there's all kinds of sensor inputs and safety processors and a bunch of stuff. So one of Elon's goals is to make it super affordable. So every car gets an autopilot computer. So some of the recent startups you look at, and they have a server in the trunk, because they're saying, I'm going to build this autopilot computer that replaces the driver. So their cost budget's $10,000 or $20,000. And Elon's constraint was, I'm going to put one in every car, whether people buy autonomous driving or not. So the cost constraint he had in mind was great, right? And to hit that, you had to think about the system design. That's complicated. It's fun. It's craftsman's work. Like a violin maker, right? Yeah. You can say Stradivarius is this incredible thing, and the musicians are incredible. But the guy making the violin, picked wood and sanded it, and then he cut it, and he glued it, and he waited for the right day so that when he put the finish on it, it didn't, do something dumb. That's craftsman's work, right? You may be a genius craftsman because you have the best techniques and you discover a new one, but most engineering is craftsman's work. And humans really like to do that. Expression.
Smart humans.
No, everybody.
All humans.
I don't know. I dug ditches when I was in college. I got really good at it. Satisfying.
Yeah.
So
digging ditches is also craftsman work.
Yeah, of course. So there's an expression called complex mastery behavior. So when you're learning something, that's fun because you're learning something. When you do something that's rote and simple, it's not that satisfying. But if the steps that you have to do are complicated and you're good at them, it's satisfying to do them. And then if you're intrigued by it all, as you're doing them, you sometimes learn new things that you can raise your game. But craftsman's work is good. And engineering is complicated enough that you have to learn a lot of skills. And then a lot of what you do is then craftsman's work, which is fun.
Autonomous driving, building a very resource-constrained computer, so a computer has to be cheap enough to put in every single car. Yeah. That's essentially boils down to craftsman's work. It's engineering.
Yeah.
It's
there's thoughtful decisions and problems to solve and trade-offs to make. Do you need 10 camera inputs or 8? You're building for the current car or the next one. How do you do the safety stuff? There's a whole bunch of details, but it's fun. But it's not like I'm building a new type of neural network, which has a new mathematics and a new computer to work. That's like there's more invention than that. But the reduction to practice, once you pick the architecture, you look inside and what do you see? Adders and multipliers and memories and, the basics. So computers is always this weird set of abstraction layers of ideas and thinking that reduction to practice is transistors and wires and, pretty basic stuff. And that's an interesting phenomenon. By the way, like factory work, like lots of people think factory work is rote assembly stuff. I've been on the assembly line. Like the people who work there really like it. It's a really great job. It's really complicated. Putting cars together is hard, right? And the car is moving and the parts are moving and sometimes the parts are damaged and you have to coordinate putting all the stuff together and people are good at it. They're good at it. And I remember one day I went to work and the line was shut down for some reason and some of the guys sitting around were really bummed because they had reorganized a bunch of stuff and they were going to hit a new record for the number of cars built that day. And they were all gung-ho to do it. And these were big, tough buggers. And, but what they did was complicated and you couldn't do it.
Yeah, and I mean,
well, after a while you could, but you'd have to work your way up because, like putting what's called the brights, the trim on a car, on a moving assembly line where it has to be attached 25 places in a minute and a half is unbelievably complicated. And human beings can do it. It's really good. I think that's harder than driving a car, by the way.
putting together, working
in a factory.
Two smart people can disagree.
Yay.
I think driving a car.
Well, we'll get you in the factory someday, and then we'll see how you do.
No, not for us humans. Driving a car is easy. I'm saying building a machine that drives a car is not easy. No, okay. Driving a car is easy for humans because we've been evolving for billions of years.
Drive cars. Yeah, I noticed
to do.
The paleolithic cars are super cool.
Oh, now you join the rest of the internet in mocking me.
Okay. I wasn't mocking. I just intrigued by your anthropology.
Yeah, it's
I'll have to go dig into that.
There's some inaccuracies there. Yes. Okay, but in general, what have you learned in terms of thinking about passion, craftsmanship, tension, chaos, the whole mess of it? What have you learned, have taken away from your time working with Elon Musk, working at Tesla, which is known to be a place of chaos, innovation, craftsmanship, and all. I
really
like
the way he thought. Like, you think you have an understanding about what first principles of something is, and then you talk to Elon about it, and you didn't scratch the surface. He has a deep belief that no matter what you do is a local maximum, right? And I had a friend, he invented a better electric motor, and it was like a lot better than what we were using. And one day he came by, he said, I'm a little disappointed because, this is really great, and you didn't seem that impressed. And I said, when the superintelligent aliens come, are they going to be looking for you? Like, where is he? The guy who built the motor.
Yeah.
Probably not, but doing interesting work that's both innovative and, let's say, craftsman's work on the current thing is really satisfying, and it's good. And that's cool. And then Elon was good at taking everything apart and, like, what's the deep first principle? Oh, no, what's really that ability to look at it without assumptions and how constraints is super wild. He built rocket ship and
using
electric car and everything. And that's super fun. And he's into it too. Like, when they first landed 2 SpaceX rockets at Tesla, we had a video projector in the big room, and like 500 people came down, and when they landed, everybody cheered and some people cried. It was so cool. Yeah. All right, but how did you do that? Well, it was super hard. And then people say, well, it's chaotic. Really? To get out of all your assumptions, you think that's not going to be unbelievably painful? And is Elon tough? Yeah, probably. Do people look back on it and say, boy, I'm really happy I had that experience to go take apart that many layers of assumptions? Sometimes super fun, sometimes painful.
So it could be emotionally and intellectually painful, that whole process of just stripping away assumptions.
Yeah, imagine 99% of your thought process is protecting your self-conception. And 98% of that's wrong.
Yeah.
Now you got the math right. How do you think you're feeling when you get back into that one bit that's useful? And now you're open and you have the ability to do something different. I don't know if I got the math right. It might be 99.9, but it ain't 50.
Imagining it, the 50% is hard enough.
Yeah. Now, for a long time, I've suspected you could get better. Like, you can think better, you can think more clearly, you can take things apart. And there's lots of examples of that. People who do that. So.
And Elon is an example of that.
Apparently.
You are an example. So
I don't know if I am. I'm fun to talk to.
Certainly.
I've learned a lot of stuff.
Right.
Well, here's the other thing is, like, I joke, like I read books. Yeah. And people think, oh, you read books? Well, no, I've read a couple of books a week for 55 years.
Wow.
well, maybe 50, because I didn't learn to read until I was 8 or something. And it turns out when people write books, they often take 20 years of their life where they passionately did something, reduce it to 200 pages. That's kind of fun. And then you go online and you can find out who wrote the best books and who, like, that's kind of wild. So there's this wild selection process, and then you can read it and for the most part understand it. And then you can go apply it. Like, I went to one company, I thought, I haven't managed much before. So I read 20 management books, and I started talking to them and basically compared to all the VPs running around. I'd read 19 more management books than anybody else. It wasn't even that hard.
Yeah.
And half the stuff worked, like first time. It wasn't even rocket science.
But at the core of that is questioning the assumptions, or sort of entering the thinking, first principles thinking, sort of looking at the reality of the situation and using that knowledge, applying that knowledge. So
I would say my brain has this idea that you can question first assumptions, but I can go days at a time and forget that, and you have to kind of like circle back to that observation
because it is emotionally
it's hard,
challenging.
Well, it's hard to just keep it front and center because you operate on so many levels all the time, and getting this done takes priority, or being happy takes priority, or screwing around takes priority. Like how you go through life is complicated.
Yeah.
And then you remember, oh yeah, I could really think first principles. Oh shit, that's tiring, but you do for a while, and that's kind of cool.
So just as a last question, in your sense, from the big picture, from the first principles, do you think, you kind of answered already, but do you think autonomous driving is something we can solve on a timeline of years? So 1, 2, 3, 5, 10 years, as opposed to a century?
Yeah, definitely.
Just to linger on it a little longer, where's the confidence coming from? Is it the fundamentals of the problem, the fundamentals of building the hardware and the software?
As a computational problem, understanding ballistics, roles, topography, it seems pretty solvable. I mean, and you can see this, like speech recognition. For a long time, people are doing, frequency and domain analysis and all kinds of stuff, and that didn't work at all, right? And then they did deep learning about it, and it worked great. And it took multiple iterations. And, autonomous driving is way past the frequency analysis point. Use radar, don't run into things. And the data gathering is going up, and the computation is going up, and the algorithm understanding is going up, and there's a whole bunch of problems getting solved like that.
The data side is really powerful, but I disagree with both you and Elon. I'll tell Elon once again, as I did before, that when you add human beings into the picture, it's no longer a ballistics problem. It's something more complicated, but I could be very well proven wrong.
And cars are highly damped in terms of rate of change. Like the steering system is really slow compared to a computer. The acceleration and deceleration is really slow.
Yeah, on a certain time scale, on a ballistics time scale, but human behavior, I don't know. I shouldn't say
human beings are really slow too. Weirdly, we operate, half a second behind reality. Nobody really understands that one either. It's pretty funny.
Yeah.
So,
we very well could be surprised. And I think with the rate of improvement on all aspects, on both the compute and the software and the hardware, there's going to be pleasant surprises all over the place.
Yeah.
Speaking of unpleasant surprises, many people have worries about a singularity in the development of AI. Forgive me for such questions.
Yeah.
When AI improves exponentially and reaches a point of superhuman level general intelligence, beyond the point, there's no looking back. Do you share this worry of existential threats from artificial intelligence, from computers becoming superhuman level intelligent?
No, not really. Like we already have a very stratified society. And then if you look at the whole animal kingdom of capabilities and abilities and interests, and, smart people have their niche, and, normal people have their niche, and craftsmen have their niche, and Animals have their niche. I suspect that the domains of interest for things that, astronomically different, like something got 10 times smarter than us and wanted to track us all down because what? We like to have coffee at Starbucks. Like, it doesn't seem plausible. Now, is there an existential problem that how do you live in a world where there's something way smarter than you and you base your kind of self-esteem on being the smartest local person? Well, there's 0.1% of the population who thinks that, because the rest of the population's been dealing with it since they were born. So the breadth of possible experience that can be interesting is really big. And superintelligence seems likely, although we still don't know if we're magical, but I suspect we're not. And it seems likely that it'll create possibilities that are interesting for us, and its interests will be interesting for whatever it is. It's not obvious why its interests would somehow want to fight over some square foot of dirt or, whatever the usual fears are about.
So you don't think you'll inherit some of the darker aspects of human nature?
Depends on how you think reality is constructed. So for whatever reason, human beings are in, let's say, creative tension and opposition with both our good and bad forces. Like, there's lots of philosophical understanding of that, right? I don't know why that would be different.
So you think the evil is necessary for the good? I mean, the tension.
I don't know about evil, but like, we live in a competitive world where your good is somebody else's,
right?
Evil. There's the malignant part of it, but that seems to be self-limiting, although occasionally it's super horrible.
But yes, there's a debate over ideas, and some people have different beliefs, and that debate itself is a process. So arriving at something.
Yeah, and why wouldn't that continue?
Yeah. But you don't think that whole process will leave humans behind in a way that's painful? Emotionally painful, yes. For the 0.1%, they'll be.
Why isn't it already painful for a large percentage of the population? And it is. I mean, society does have a lot of stress in it about the 1% and about the this and about the that. But everybody has a lot of stress in their life about what they find satisfying, and know yourself seems to be the proper dictum, and pursue something that makes your life meaningful seems proper. And there's so many avenues on that. Like, there's so much unexplored space at every single level. I'm somewhat of my nephew called me a jaded optimist. And so
there's a beautiful tension in that label. But if you were to look back at your life and could relive a set of moments, because they were the happiest times of your life outside of family, what would that be?
I don't want to relive any moments. I like that. I like that situation where you have some amount of optimism and then the anxiety of the unknown.
So you love the unknown, the mystery of it.
I don't know about the mystery. It sure gets your blood pumping.
What do you think is the meaning of this whole thing, of life, on this pale blue dot?
It seems to be what it does. Like, the universe, for whatever reason, makes atoms, which makes us, which we do stuff. And we figure out things and we explore things, and
that's just what it is.
It's not just.
Yeah, it is.
Yeah.
Jim, I don't think there's a better place to end it. It's a huge honor. And
well, that was super fun.
Thank you so much for talking today.
All right, great.
Thanks for listening to this conversation, and thank you to our presenting sponsor, Cash App. Download it, use code LEXPODCAST. You'll get $10, and $10 will go to First, a STEM education nonprofit that inspires hundreds of thousands of young minds to become future leaders and innovators. If you enjoy this podcast, subscribe on YouTube, give it 5 stars on Apple Podcast, follow on Spotify, support it on Patreon, or simply connect with me on Twitter. And now, let me leave you with some words of wisdom from Gordon Moore. If everything you try works, you aren't trying hard enough. Thank you for listening and hope to see you next time.